A1 is equal to 2, 1, A2, which is the second column, this is minus 1, minus 1, and A3, this is equal to 0, 3. So here we observe that we have 3 different columns, and all of these, they belong, so we can say that all of these, we can write this, these are subsets of R squared. We call these subsets of R squared because any point is represented by a pair of numbers, okay? And these pairs of numbers, we can show them in a graph like this. So the first point is 2, 1. So 2, 1, we can find it here 1, 2 along the x-axis, and for the y-axis, this is minus 1, minus 1, which is here and here. So we have, and 2, 1 is also. So we have this vector and this vector. So this is the one point defined as in here, this is the other point, and the final point is 1, 2. We need to put the this is the 3, 0, 3, this is the third vector. So we randomly assign 3 different vectors, and with these, what we can do here is I'm afraid if I forget something, we should never forget that these we can simply calculate them. So we can do C1 times A1 plus C2 times A2. We get some points, okay, where C1 and C2, they are real numbers, okay, just real numbers, including the 0. Including the 0 is important. But now, initially, I want to ask you this question. Let me see which part of the board is more efficient. Let's write it here. What is the union of points defined by C1, A1? So, if you have set A1, let's see what A1 was. A1 is 2, 1, so it is vector here. So, assume for a moment, if C is equal to 0, then CA1 is equal to 0, 0, right? Then if C is equal to 1 over 2, then CA1 is equal to, what is it? Joey, what are you going to get here?
1 over 2.
That's right, 1 over 2, 0.5. So we get this point here, which is going to be this one. We have the 0, we have this, and then C can be 1. What is Joey? What is CA1? So assuming the constant C is 1, what is C times A1?
2, 1.
2, 1. Okay. So we have this point. And similarly, we can assign C is equal to minus 0.5, we get minus minus, so we move to 1, 0.5, so we get this point here, and then we're going to get minus 2, minus 1, and so on. So what do you think you can draw with this point that are on the board? What are we spanning?
A straight line.
That's right, so we have a straight line, and what is the dimension of a line? It is one-dimensional structure, or one-dimensional set. Now, what could be, so here we have another question, and this is the question we can follow with Teddy was after Joey. Okay, Teddy. So, okay. What is the union of points represented by C1A1 plus C2A2. What is the unit of points that can be described by this combination? So A1 is 2, 1, is this vector. A2 is minus 1, minus 1. We're talking about this vector here. Any idea?
I think it's a point, 0.
Well, you're right. Actually, the first thing we have to notice or to figure out is to identify whether the 0 is in this among these points. Now, since C1 and C2 they include the 0, we can say that yes, this is a choice. So let's do this in red. Let me find another pen. So here, this doesn't right. Our options are getting less and less. So this point is one of the interesting one. Another point is where we set, let's say, C1 and C2 is equal to 1. C1 is equal to C2 is equal to 1. What do we get in that case? We get 2, 1 plus minus 1 minus 1. And this would be equal to 1, 0, right? So 1, 0, we get this point here. We can also assign C1 is equal to 2 and C2 is equal to 1. In this case, we get what? 2 times 2, 1 plus minus 1 minus 1. So this base is 4 minus 1 is 3, 2 minus 1, 1. So we get another point, 3, 1. So it's here, we get this point. Okay. Can you see do you see a pattern between the points that can be identified by A1 and A2? So here we have 4, 2. This is minus 1. Plus 1, 1, this is going to be 5, 3. 1, 2, 3, 4, 5, 3. We get also another point around here. So it looks like, so what options can you suggest, Vivian? Could this be a line or a plane?
I think it would be another vector.
Okay, but another vector. Normally, let's not forget that A1 and A2, they are both vectors, okay? And we are using 2 vectors to move around, okay? And imagine that these numbers can change a lot. We could say that this would, what about if we ask the rest of the class? The union of these points, what can we construct with these? Let's ask Talha, can you answer this? We are offering 2 options. It would be a line, a straight line, which is 1-dimensional structure, or a plane, which is 2-dimensional. Talha, do you have the microphone ready? Okay, we go to Silvio. Silvio, what would you suggest? What could it be?
I don't know.
Can I answer?
Yes, please.
Since we're joining 2 lines together, it's gonna form a plane, I think.
Yeah, okay, that's right. It's going to be a plane, it cannot be a line, because line is excluded the moment that we see that they are not in one line. It is this point that we see here, so you can take out the possibility of having a line. So the unit of points defined by these 2 vectors would create a 2-dimensional set, dimensional. So this would be a plane. A line is 1D, so we can write this one 1-dimensional. A plane is 2-dimensional. Now, another combination could be the following. What combination? Let me ask another question. What is the union of A1, or let's write them like this. A1 is 2, 1. Then we have minus 1, minus 1. And 1, 0. So here we have 3 vectors. what could be the union of all the points that can be scanned by these three vectors, which is defined as finding any point AB, which is equal to constant C1 times 2, 1, plus constant C2 minus 1, minus 1, plus constant C3, 1, 0. So, Teddy, Tanya, Silvio, Shevchet, what do you think about this?
I think it will be 2, 0.
2, 0, like what? I mean, 2, 0 is one of the points, which means that 2, 0, where is it? 2, 0 is this point here. Let's make a square. Okay. But this is the case if C1 is equal to C2 is equal to C3 is equal to 1. Okay. So that's one point, that's for sure. Give me another combination of C1, C2, and C3. What if we assign this 1, 0, 0? What point do we get?
3, 3, 1.
Or 2, 1?
There are 2 zeros. Okay, 2, 1. Sorry.
Okay, then we can put here 0, 1, 0. What would be the answer?
-1, -1.
-1, -1, which is this point here. We're doing this in squares. So once you see this, could they be in the line, these 3 points? The squares, the black squares. No, right?
No, they are not. Yeah.
They're not, okay. Then another option is 0, 0, 1, which means that we get a point of 1, 0. The point 1, 0 is here, okay? And then we can come up with some other combinations. But if we change these numbers again, I mean C1, C2, and C3, what do you think we are scanning? What are we going to construct if we put all of these together?
3-dimensional. I think it will be
A plane.
3-dimensional.
Actually, if it is 3-dimensional, that means that we have to get out of the board. So the board is 2-dimensional. If you're talking about 3D, we cannot draw it correctly here. So, any opinion? Anyone else in the class? So, with these vectors, first of all, we have to notice that these 3 vectors, they are all a subset of R squared, okay? Which means that we have a pair of numbers, which is going to determine where we can find a specific point. But one thing that we can also notice is that this vector, can you write this vector as a function of the first 2? We can ask Sergio. What do you think, Sergio?
I think those points are 2-dimensional.
They're 2-dimensional, but if you look carefully, actually, for the vector 1, 0,
Multiply by 2.
is the summation. If you sum the first one and the second, you get this, right?
Yes.
Okay, so if this is the case, we can write it like this. This can be C1 times 2, 1 plus C2 minus 1 minus 1 plus C3. And here we can write here, maybe, let's write it like this. This is C1A1 plus C2A2 plus C3A1 plus A2, right? Because the third one is the summation of the first 2. If we do it like this, we can see that any point, it can be described by A1 and A2. If this is the case, we get a 2-dimensional structure, or we get again a plane, okay? We get a plane. Now, this is something that we can learn, and then we can also define some sets of points, which could be as follows: 1, 0, 1, 0, minus 1, 2, and 3, 1, 1. So if we have these 3 points, and the linear combination of these 3 points, what can we scan with these? We can ask, actually we had one Rubin that commented, I don't remember who was. Let's get them.
Speaking.
Rubin, Aga, was it you?
Yes.
Then let's go to Tsanay or Rubini Dush. So what can you spend with these three vectors that are shown here? Rubini?
Professor,
No comment?
are these three-dimensional and we can represent it on board?
They belong, actually, if you think about the Cartesian coordinate system, we can define an x, y, and z. So each one of these is a member of R3. Okay, so we have a triplet of numbers to determine each point in here. So these three vectors, the combination of these, what can we define?
We can define a 3D space.
Exactly, okay. We get a three-dimensional space. So it's one higher dimension than a plane. Okay, we can do this with three vectors. So then, since we're dealing with this, I think we know now how we can combine two vectors. We add them together, we can subtract them, and we can do anything, right? It's relatively easy. The part of adding and subtracting different vectors. But now let's think for a moment what could be. Actually, before we go to this other topic, we see here that there is a matrix A on the board. Okay, what is the dimension of A? It's 2 by 3, right?
Yes.
And if I can have helping here, Ray Kurti, what is A transpose? Ray, can you answer?
May I answer?
I'm sorry, Professor, I'm having internet problems and I can't even hear you properly and I don't read the board.
Or you cannot read the board, okay.
May I answer?
Well, it happens, Ray. Sorry about that.
Can I
Not a
answer?
problem. I just had video problems and I can't hear a full sentence you say.
Okay, I hope students like you are a minority here. I hope that I can. But Ray, I hope it does improve after a while. But yes, I had a request to answer. So yes, you can speak.
Okay, the first row will be 2, 1.
The first row. Okay, so you are saying the first row is 2, 1. So you are picking the first column and you are making it a row, right?
Yes.
Okay, that's true. So transpose, you take the first column, you make it a row, and that's how you do it. What is the next row?
-1, -1.
-1, so you pick the second column, you make it a row. This is what transpose is about, yes?
0, 3.
0, 3. Okay, that's good. At the same time, one can also say that you take the first, okay, this is gone. You take the first row and you make it as a first column. This is also what you look at it. But in principle, this is what transpose is about. We are making a matrix which is now 3 by 2. Okay. Now that we have this, we know the transpose. What do you think? Can we multiply A1 with A2? A1 times A2, and A1 and A2 they are here. After Ray, we can have Regi. What do you think, Regi?
Yes.
Okay. What would be the answer?
-2 -1.
No, A1 is here. It's 2, 1, right?
Yes.
What is the dimension of 2, 1?
1, 2.
It's 2, 1. It is 2 rows, 1 column. And we want to multiply this with A2, which is -1, -1, which has a dimension of 2 by 1 also, okay? So what do we
It cannot be multiplied.
That's correct. So we cannot multiply because this is not defined. Okay, this is not defined because these dimensions don't match. Okay, so it is not possible. But in order to make this possible, what do you think we can get if we multiply A1 transpose times A2? What is A1 transpose? Yeah, Reggie, you can continue.
A1 transpose is
It's 2, 1. You make the column, you make it a row. That's it, okay?
okay, yes.
Because A1 was this, and now that we make the transpose, this is 1 by 2. If this is 1 by 2, we multiply this one with a matrix which is minus 1, which is 2 by 1. And is this multiplication defined?
Yes.
Yes. So these two elements are equal. So what would be the result here? What is the dimension of the matrix of the result here?
1, 1.
1, 1. That's correct. 1 by 1, yes. And can you give me the correct
1 by
answer?
1.
So this is 1 by 1. So we get a scalar. 1 by 1 matrix, it's a scalar. It's just a number. It's not a vector. Okay. So this is how we can denote these two. And what is the result?
Minus 3.
Minus 3.
Minus 3. Okay, that's correct.
Minus 3.
So this product between two vectors, we call this one inner product. Okay, this is the inner product, or dot product, or scalar product. You are going to see these a lot in physics. So once you do in physics, you are going to calculate that work, which is measured in joules, which is a scalar quantity. It does not have a direction. So once you say that your energy bill is 700 kilowatt hour, it's just a number. It doesn't have any dimension. So we said that this was not defined, and here you said it's minus 3. That's correct. And this one we call inner product. Inner product or dot product or scalar product. Product scalar, resultado de number e vector. So this inner product, we denote this one like this. A times B, this is equal to A transpose times B. But assuming that A and B are both vectors, okay? So this is the inner product. And now we can also calculate the inner product of a vector with itself. So for example, what is going to be A1, A1? A1, A1. So we can have after Regi, Marvi. What do you think, Marvi? So what would be the result of A1 with A1? We want to calculate the inner product. Marvi, can you? Yeah.
Yes, I couldn't hear. Yes,
Yes,
what was the question?
what would be the inner product of A1 with itself?
2, 1 times.
Yes, but we have to be careful. This is a row, right? 2, 1 multiplied by 2, 1. This would be equal. We multiply this row with this column carefully, and we get 2 times 2 plus 1 times 1. We get a 1. We get a 5. What about if we take the inner product of this vector with itself? What is the inner product of this vector?
5.
It's 5, that's true, it's also 5, but to write it, we write it something like this, and we say 0 minus 1, 2. We multiply this with 0 minus 1, 2 again, and this will be, we do element-wise 2 by 2 multiplication. So we have 0, 0, minus 1 plus minus 1 is 1, so we get 0 plus 1 plus 4, we get another 5, okay? So this is the inner product. Now, so after we define the inner product, we can use it to do the normalization of vectors. Normalization of vectors is very important in several algorithms or techniques that you will need to develop later on, because sometimes we want to compare the same type of data, but the data can be at different orders, okay? It can be different, for example, let's assume for a moment a series of numbers. So we have here 1, 1. This is a vector, okay, 1, 1. And we can have also 2, 1. Or at the same time, we can have 198, 99. This is another vector, and we can also have 3004, 1007. Now, here we have some vectors that we want to compare them and to see whether they represent a specific type of data. Now, what is the magnitude of the first vector? Actually, the magnitude, sorry, I think we have not defined the magnitude yet, sorry. So far, we checked.
2.
It's my mistake, I forgot that we didn't cover the magnitude yet, but we know the inner product, right? Now, the magnitude, and let me ask you, for example, who is Marvin, do you know what is magnitude in Albanian? Would you translate it? Madhësi, po e vërtet është madhësi. Nëse është një madhësi vektoriale, është sa e gjatë është vektori. Kjo është madhësia. Okay, kjo është përkthimi shpejtatim të. So the magnitude, this is defined as for any vector A, this is the magnitude, and at the same time is defined as a square root of A transpose times A. Okay, so this is the magnitude. So after the inner product, we define this, which means, for example, what is the magnitude of A1?
5.
No.
Square root of 5.
Then I have to have Kledion following me after Marvin. So Kledion, it looks like the magnitude of A1 is equal to square root of 5. Also, the magnitude of this other vector, which is a point in R3. This is a point in R squared. This is R cubed. So both of them, they have the same magnitude. Now that we have the magnitude, I can ask you the following. So what is the magnitude of this vector 1, 1?
Square root of 2.
Square root of 2. That's right. So the magnitude of 1, 1, we can write it like this. The magnitude of a vector which is 1, 1 is equal to the square root of transpose of this 1, 1. And the transpose of 1, 1, we can write it like this, times the vector itself, square root again. We have 1 plus 1, 2. So this is square root of 2. That's right. Square root of 2 is approximately 1.4. Okay. So the magnitude of this vector is around 1. What is the magnitude of the vector 2, 1?
5.
Square root of 5.
Square root of 5.
5, yes.
5.
So the magnitude, let's call it square root of 5, but the magnitude of this vector, it is 10 to the power 0. It's 1.4, okay? The magnitude of the second vector, this is also something like 10 to the power 0. It's 1 to 2. So that's what we should care. The first thing we should care is the order of magnitude. Of course, it's important for us to know that it's 1.4 versus 2.3, but 1 to 2 or 1 to 5, we count it as 10 to the power 0. Now we have this other number here. What is the magnitude of this vector? This looks like something like 10 to the power 2. Because what is the magnitude here? The magnitude is 198 squared plus 99 squared, square root. The numbers will show up like around 200 squared. This is 4, 1, 2, 1, 2. Plus 100 squared, 100. How much would it change? This would be Is it correct, or am I doing something wrong?
It's correct.
50,000. The square root of 50,000 is something a little more than 220 something. So, but we are around 10 to 10 squared, 10 to the power 2. When it comes to this other vector, the magnitude is around 10 to the power 3. So often, when we want to provide, or when we want to ask for data analysis, automatic comparison between two huge data sets, or it could be between two images, which are also complex input data. Sometimes we might want to say that how much similar is this vehicle with this other vehicle. And to do that, we often need to extract a feature vector. Okay, this is a keyword which you need to write it down. So we can have a feature vector. And feature vectors, for example, we want to compare, imagine that you have a vehicle and it's a self-driving vehicle, and what it does in order to drive alone, it has to continuously, it receives images, but images are an array of numbers. And in order to understand that it's a tree or a person, it continuously tries to extract feature vectors. The feature vector can be the same thing, but it could be of different magnitude. In order to compare those, often you may assume this as if, so we know the magnitude, let me take this out. So let's assume that we have a circle with radius 1, okay? This is 1, 1, minus 1. And then we have a vector which is 2, 1, which is somewhere here. And we have another vector which is located at 3, 1, 1, 2, 3. So we have another vector which is around here. And then we have another vector which is 1 minus 1, which is this vector here. And we can have 1 minus 2. Right, so we can have these vectors here. Normally, once you look at these vectors, we can also have a vector which is 200 by 300, which is going to extend beyond the board. So we can add also another vector around here, which can be like this. And these feature vectors, or vectors in general, they might represent a specific object or specific behavior. And often, we may want to cluster these or to classify these. One careful observer could say that we can have a lot of vectors that extend like these, okay, and also like this. And one can say that we can cluster these vectors, like these three here, they belong to the same category, okay? And also we can see that these vectors here, they are closer with respect to each other, and how close two vectors are, we judge them by the angle that is between those, okay? So two vectors that have an angle of around 0 degrees or 1 to 2 degrees, we see that they are very similar. But if the angle is huge, they are representing a vector probably in a new basis, or in a new, you may even need to have an extra orthogonal coordinate system in order to define something. So once we look at these vectors here, one can easily try to identify that we can cluster depending on these specific properties. And the graph shown on the board, we can cluster them or classify them into 4 different classes. So these seem to be similar. They belong to another class. They belong to another class, and this is alone another class. So we have 4 classes for these vectors. Now, in order to easily compare them often, after so using inner product here, we find the magnitude, then we get the feature vectors, and then from here, we want to do normalization. Normalizăm situația. Now, what normalization, this is defined, the first sentence, the previous sentence was a small joke, but the normalization is the following. For any vector A, we find a unit vector which is denoted as UA along vector A, okay? So this is the normalization. So in order to compare different vectors, it is best to normalize them, which means that this vector extending this way to keep unit length 1, we preserve the direction, but we draw this up to the radius, which has a radius of 1, okay? So unit length of 1. So here, we normalize this other vector, we end up here and here. Similarly, we normalize this one, we get this. We normalize again, we get this. And I think you can easily follow the pattern. And now that the vectors are normalized, all of them have the same equal magnitude. It is easier and better to, to compare them and to check whether they have any similarity. Because as we saw here, for example, the data, let's see, these two vectors, there is some indication that they are very similar to each other. Because 2, 1, it creates an angle with an arc tangent 2 to 1, okay? So what is this 2, 1? What is this angle? Can you help me here? What is this angle theta, which is between the x-axis and this vector 2, 1? How do we find this angle?
We can find the sine or cosine, then we can find the...
We can also relate it with a slope. What is a slope? Piercia. Piercia è funzione. Slope, it can be defined as the tangent of the angle theta, and the tangent is equal to the opposite side. Okay, what is the opposite side? If this is the angle, opposite side is this. Okay, which is equal to 1, divided by the adjacent side. Adjacent side is a side which is closer to the angle. So this is the angle, opposite side is this one, and the adjacent side is this one. So in this case, the opposite side is 1 divided by 2. Okay, and this angle theta, this is going to be equal to arc tangent, and with arc tangent of 1 to 2, we can also define this one as tangent inverse 1 to 2. Okay. And now, this is 1 to 2, if the vector is this one here, 2, 1. Okay? And now, if we consider the other angle, which is defined as 198, 99, we can also, we notice that this is equal to the tangent inverse of 99 over 198. So, if we normalize these two vectors, which are two orders in magnitude different from each other, because this is 10 to the power 0, and this is 10 to the power 2. Normalizing them and then comparing it would be much more easier for us to compare. So, good examples that I can add from here is the following. For example, if you have a certain data set, I can provide several examples, but I need to provide a few sentences to explain it clearly. But I can say this: you can extract one feature vector for a data set, and you save it. Then you can generate another feature vector, and one of them can be 10 to the power 0, the other one is 10 to the power 2. Okay? And then we have to merge this together and to make them to construct another feature vector, and we will need to normalize that one too. Okay? So if this is the case, this will make it possible for us to compare different data sets or to extract certain features. So now, let's see an example here. Let's try to identify a unit vector, UA, which is along the A. The unit vector along a specific direction, but let me think, let's try to use the board in a better way. So this unit vector, this is unit vector along the A. This is defined as a vector A divided by the magnitude of A. So this is how we find this specific, so let's call this one the definition of a unit vector. Now, in several textbooks, you might notice that the unit length vectors like maybe you've seen this. There is this I, J, K, right? So they denote often. There is a terminology which is like for the in the x-axis you have this unit vector, along the y you have the j, along the z you have the k, and something like this. And now let's see an example. Let's try to identify. So over the board we have, you can follow the definitions, the different definitions that we have offered. So let's pick the first column of A transpose here. So this one, the A transpose, the first column, or let's call it A. Okay, let's assume it's 2 minus 1, 0. With this, I can ask. I remember where Clédion. I think I talked with Clédion. Claire, can you help me here? So, how can we? What is the magnitude of this vector A? It looks like everything is going to end up in the same number. Claire, can you use a microphone and already set?
Yes.
Okay, so what is the magnitude of A in this case?
The negative of A?
The magnitude. Magnitude, we have defined it right here.
Yes.
So it's going to be the square root of the transpose of this A, 2 minus 1, 0, multiplied with 2 minus 1, 0 again.
Multiplied. Okay, wait. Wait a second.
Okay.
It's going to be 5?
That's the inner product. The inner product is 5. The magnitude is the square root of 5.
Okay. Sorry.
Okay. So let's not forget this. So, yeah. So this is going to be equal to square root of 5. And here, we can say that this is 1 over the square root of 5. This is
Yes.
1 over the magnitude.
Yes.
Times the vector is 2 minus 1, 0. 2 minus 1, 0. And then
it's going to be 2 over square 5.
That's right.
And minus 1 over square 5. And 0 over square 5.
Yes.
0. Yes.
That's correct. So here we use a property that any constant multiplying with a matrix, we multiply with a constant each element of the matrix. Okay, so this is how we can generate the unit vector. Now we are dealing with vectors, and then we can also try to identify, let's say, what is the angle between the columns of A. Okay, we see here that we have the A, and I think probably we can erase this part, or let's do the magnitude a little more. So we can also define the following. The dot product between A and B, it can be defined as the magnitude of A times magnitude of B times cosine theta. Okay, and now let's assume that we have the vectors here. A is the first column, B is the second column. Then I can ask for help from Claudia. So Claudia, what is the magnitude of B, or what is the magnitude of this vector?
It's the square root of B transpose.
Yes.
Multiplied B.
So this B, this means that the magnitude
Square root 11.
Square root of 1 minus 1, 3. Okay. We multiply again 1 minus 1, 3. And the square root. So what do we get here? And let's not forget, this is the inner product of the same vector with itself, right? And here we get, so can you help me, Claudia, what do you get after this?
Square root 11.
Square root of what?
11.
11, okay, that's true. So this is square root of 11. But then also, let's say that this dot product here is in fact the product of A with B. So what is the inner product of A with B? The inner product of A with B is, we get the transpose of A. A was the first column here, right? So we do here 2 minus 1, 0. 2 minus 1, 0. We multiply this with B, which is 1 minus 1, 3. Okay? And this is equal to, let's probably, I can ask help from someone else, not Claudia. Claudia, can you help me here? So what is the magnitude of A? So here we have one identity, so this is true. But now we want to find the cosine. And from the cosine we can calculate what is the angle between the two vectors. Oh, I don't know if Clyde has any problem with microphones or the service. Clyde, we have only one Clyde, okay? Okay.
It's square root of 3.
Square root of 3. Which one? The magnitude of A?
The result of A and B, the product.
Oh, no, okay, you mean this one, right?
Yes.
Okay, let's check. So this is 2 plus 1. Yeah, that's true. This is, what is this? Square root of 3?
Yes.
But no, we are finding the inner product, so it's 3.
Oh, okay, okay.
So this is 3 is equal to, by the way, what is the magnitude of A?
Square root of 3?
Square root of 5. Okay, so it's on the board, sorry, you cannot see it for the moment, but now you can. So this is equal to the square root of 5. And what is the magnitude of B? We got square root of 11. Okay. And this is equal to cosine theta. So the angle between these two, so we can write this again, this is equal to square root of 55 cosine theta. So then we can say that cosine theta is equal to 3 over the square root of 55, and this implies that the angle theta is equal to the inverse cosine or arc cosine of 3 over square root of 55. Or similarly, we can write this one, that this is equal to the cosine inverse, okay, of 3 over the square root of 55. So this way we can find the angle between any two vectors. Now, following a similar path, so what is the inner product between A and B? Casey? Casey, can you help me here? What is the inner product of A and B? Casey, if Casey cannot...
should be 0.
Should be 0. Okay, what about Yonet? Can you help me here? Yonet, Hamzalari? It should be 0.
I can't see the video quality.
Sorry?
I cannot see the video very well.
Okay. Do the others see the video very well? I'm afraid this is a common problem, but I hope it's not.
I see it well.
You see it well? Okay. Okay.
I fixed the settings too, but I don't know why.
Yeah, it might be, you know, sometimes you can select in the settings, you can adjust the incoming video quality setting.
Yeah, I did that. I did that, but I still can't see it.
Don't worry. Sometimes the internet, it might fluctuate the strength of the signal. Yeah, or maybe the router can be in the next room. Sometimes it happens to all of us. But now, with this AMD...
Professor.
Yes.
Sorry, I have a question for the previous exercise. Why we write cosinus theta in equal to arc cosinus?
Well, these are inverse functions. Okay? They are inverse functions of each other. So, let's say, let's clarify this. So, we have this. F of x is equal to y, okay? We can multiply both sides of this identity, of this equality. We can multiply with f inverse, okay? And what we get f inverse of f of x, okay? Now, f inverse of f of x, they are inverse of each other, so this is equal to x. And at the same time, this is f inverse of y. Okay? Now, tell me, I think we know with infinite precision, we know what is, let's say, the sine of 30. So if we have an angle of 30 degrees, we know that if this is 30, or let's say the cosine of 60. The cosine of 60, let's write this here, is equal to 1 over 2. Okay? Now, we can also say that we can multiply both sides of the identity with cosine inverse. And cosine inverse with arc cosine is the same thing. In calculators, you might find this cosine inverse, or cosine to the power minus 1 and arc cosine. So, is it clear? Or I can continue, I can finish this up. And so here we have cosine 60 is equal to 1 over 2. And we can multiply both sides with cosine inverse times cosine of 60. This is equal to cosine inverse of 0.5. Now, cosine inverse with cosine, they are cancelled, which means that the 60 is equal to cosine inverse of 0.5, which means that sometimes we might be given the value of the cosine and we need to identify the angle. So that's why, that's where we may apply inverse functions. Is it clear?
Yeah, it is clear.
Yes? Okay. Thanks, Indrid. Okay. Then, so these are the inverse functions. And now, a similar idea, this also operates with the matrices. So we have a matrix, we can do the following. So we're going to solve examples like this a lot. If we have a matrix times x, this can be equal to b. And you know matrix multiplication. Let's assume that A is 3 by 3, x is 3 by 1, b will be another vector which is 3 by 1. Now, if we multiply both sides of the equation with A inverse, what we get is that we get A inverse times B. And now A inverse times A is equal to what? Is equal to the identity matrix.
Yes.
We did last time, right? So here we have identity matrix, which is a square matrix, it's 3 by 3. We multiply this with the vector x, and this is going to be equal to A inverse times B. What is identity matrix times x?
It's x.
It's x itself. It doesn't change anything because it's just multiplying each component of x with 1, okay, nothing else. So x, it can be equal to A inverse times B. So now, the matrices, the inverse of the matrices, it is equivalent to some degree or fully with application of the F inverse or cosine arc cosine. So this is how we can work with these, or at least that's what cosine inverse was. Now let's come back here. Allow me to erase this part because probably I think yes, you might have started this in calculus. Like have you started Gauss f of g of x? Have you started this?
I've studied them before mature.
Okay, so it's high school class material. That's good. So now we're asking here A and B, inner product with A and B. A is 3, 1. 1, 2, 3, 1, it's here. B is minus 1, 3. Minus 1, 3 is minus 1, 1, 2, 3. So it's this vector. Just like the geometric representation or where the vectors are, so this is 3 to 1, and this is minus 1 to 3. Actually, you can draw squares here, so this means that this angle is 90. If this angle is 90, what is the cosine of 90?
0.
0.
The cosine of 90 is 0, which means that this inner product, it is expected to be 0. And of course, if we check, we get here the transpose of A, this is always what goes on, times minus 1, 3, and we get here 0. Okay? So these are some applications of the inner products of the vectors. Now, so we know what we are doing so far, but just as a small reminder is that the vectors, we should know also how to add them or how to subtract them. And in order to do that, I guess so here we can have a vector A, and we can have another vector B that is shown like this. Now, how can we add these two vectors, A plus B? All we do is that we try to put the vectors one by one after the other. So we can carry this vector from here and bring right here, but we have to bring the end of the vector B to bring it at the tip of vector A. So this is the end of vector A, this is the tip of vector A, and we carry on the B like this. And this is the end of vector B, and this is the tip of vector B. So adding them up together will result from the end here to the tip of the last vector. So here we have A plus B. Okay? And now, when we look at this, we can tell a lot of things. We can say that the direction of the let me think for a moment. Yeah, the direction of a vector that passes through these 2 points, it can be determined correctly by the A minus B, okay? And we can, regarding this, we can go over an example and see. But before, okay, so we're just talking for a moment about vector addition. In fact, in the previous few minutes ago, I think we talked about, let's make a short note here. we said that a line L1, this can be defined as a vector P plus any constant C times T, where T is a vector, okay? And a line L2, it can also be defined as C times T, where T is a vector, C is a constant. Now, which one of these two lines includes the origin?
Second.
The second one. So in the second one, we include the origin, but the first one, it doesn't. So in fact, these two lines, L1 and L2, what they have in common is that they are parallel, okay? They are parallel, but the relationship between those is that L2, any point of L2, it has been shifted up with a constant value, okay? And this constant value is a vector P. Now, let's see an example that might help us to understand. So, let's assume that we have a graph with points. We have 2 points, where we have point P1, which is located at -1, 1, and the point P2, which is located at 3, 2. And if we try to draw this, it's going to be something like this. The first point, -1, 1, it's here, -1, 1. And the other point is 3, 2. This one is 1, 2, 3. 2 is somewhere here. Okay, here we go. So this is point P1, this is point P2. Now the question is the following. Let's try to identify a line equation which passes through point P1 and P2. Okay? How can we approach the solution of this problem? I can ask Indriti. Indriti?
We can try to change the value of the first vector, so it is the same as the second vector.
But
so -1, 1 is equal to 2, 3. -1, 1 times x is equal to 2, 3.
So you're saying, so repeat my question. So the idea is that our objective is to identify the equation of this line, which passes through this point here and this point here.
We should take a common point first.
Change vector 1 into vector 2.
We can subtract them, right? Because we have one vector which is pointing like this, and one vector which is pointing like this, and we can try to do this. What is P1 minus P2? Okay, how can we do this? P1 is this one. Minus P2 is going to be a vector which extends like this, okay? And we know how to add vectors. We start from 1, we go to the tip, then we put the end of the second vector at the tip of the first one. I hope you can see this clearly. So this is the tip of this is the other vector. So in principle, P1 minus P2 is this vector, which is over this line. Okay? So if we do this, we can identify, so let's see what we get. P1 is -1, 1, minus 3, 2, and we get, what is this equal to? -4, -1. Okay? So this is a vector which points along this direction. And now, what did we say? We said that if for example, these two vectors here, L1 and L2, they are parallel to each other. The only difference between them is this constant vector P. Now, let's not get confused. P1 here actually is a point, so we could use another letter. But for here, this is what we can say. We can also consider the following. We can say that P2 minus P1 is fine, no problem. So if we do P2 minus P1, we get 3, 2 minus 1, 1, and this will be equal to 4, 1. Okay, so the first one, it determines this vector pointing downwards, and this other one, it points another vector pointing in the other direction, but also the sign is changing. So, okay, so we found at least the direction where this is passing through, and we need to identify P. So the next question is that we need to identify P. What is P? In order to do this, actually we can even consider the following. We can say that the line that we are interested, it can be equal to this point as a reference, minus 1, 1, plus a constant C times 4, 1. Okay? And so this is doable. So we found the solution or the equation of a line which it passes through these 2 points. But the important thing initially, it was being able to identify the slope. And actually, let me ask you, what is the slope of this line? Saj Garcia. Holti, can you answer this? 3. How did you find this 3? So slope është tangjentja e këndit. Sa është tangjentja e këndit?
Slope is fine between x2 minus x1 divided by y2 minus y1.
That's correct.
I mean, that's how I remember in high
That's
school.
true. That's true. But we can let me write it here. So we can say that the slope is equal to the tangent of the angle theta with respect to x-axis. So this is the slope. We're asking about this angle theta, and this angle theta is going to be, let me think for a moment, because you are right. You said we do the change in y divided by the change in x. Sorry, I moved this one too much up. So I did not, unë nuk e pash se kush foli, po kishte drejt. Në fakt që the delta epsilon për delta x. So this is equal to delta y over delta x. And this, what is this side, the length? It's 1, okay? Divided by the delta x. What is delta x?
3.
4. That's true. So this is 1 over 4. So this is the slope. So what is the angle? Is the angle more than 45 or less than 45? How do you, so if the angle is 45, what is the slope?
It is 1.
It is 1, that's true. This is, let me write this down, when the angle is 45 degrees. Now, here, we observe a slope which is 1 over 4. This means that we have a very small angle, something like this. If we are somewhere here, what is the slope here? Is larger than 1, okay? Here, which is this line here, the slope is smaller than 1. And if we know the slope, which, can you see this part? It looks like there is some reflection, or is it only me? So, if this is the slope 1 over 4, we know also that the equations of a line, they can be written as y is equal to mx plus b, okay? Where in this case, y would be m would be 1 over 4 times x plus b. And the next question, one of the challenges would be to be able to determine what is b. How can we do it? Forty, can you help us here? You can think this as a homework. This problem.
Professor, can't we express the equation of a line as epsilon b minus epsilon y is equal to m xb minus xy? And this way we can find the b.
Yes, that's true. That's also possible.
Can we plug x and y for example, 3 and 2?
Yes, let's do that. For 3 and 2, that means that x is 3. So this is the equation. And then y is equal to 2. 2 is equal to 1 over 4 x plus 3. So here we have 2 minus 3, it's minus 1, is equal to 1 over 4 x. X is equal to, wait, no, I made a mistake. I made a mistake. I should substitute in x. That was complete unacceptable. So y here is equal to 2, and this is equal to 1 over 4 times x. What is x? It's 3 plus b. Because in this equation, we know m. We did it, okay? I don't know, can you see this part? We know m. And then now we need to know b. So let's substitute these values, and we get here 2 is equal to 0.75 plus b, which means that b is equal to 1.25. So the complete equation is going to be the following. This is 1 over 4x plus 5 over 4. Is it correct? Yeah, this is it. This is equal to y. Okay, so these are the equations of lines. Now, at the same time, we can determine the... Just give me 1 second, I'm just checking something very fast. Okay. Ty bëziska është duket mirë drasa?
Po.
Këtu që jam në klasë, nga që është erësuar pak, unë nësi e shoh edhe që përshkruaj, po kamera si duket bën atë autofocus ose autocorrection, contrast enhancement, ju e shikoni çik më mirë sonë. Se është drasa e bardhë, po këtu me vërtetë kam çik habitën se shihim, po e shoh në ekran duket veçanë mirë. Okay. These were the equations of a line. Nëse më vret sytë edhe ekranin bën shumë dritë, këtu drasa është natë, është errësirë me fjalë. Kur isha në leksion semestrin e kaluar, që ishte ndodhi pandemia, kur keni qenë në shkollë mesme, kisha leksion me një grup studentësh, por ishte klasë e mirë të vitit 3. I thash më thoni të vërtetë, thash sa për jush, ndërkohë që vazhdojmë mësimin, po shikoni telenovelën e orës, se ka një orë caktuar. Po person tha në tregat e studentë, më thon drejtë tha, telenovela po shohim. Po e thash, it can happen. Ka njëri që po shef lulet e vetmuara tani apo?
Jo.
Okej, 2 vet tani o drejtani, po tjerët.
Ja.
Ska shans. Okay, so here, this is the line equation. Now, let's think for a moment about the plane equation. Now, the plane equation, we know that we can have C1 times T plus C2 times V. So, we know that for a plane, since we need 2 dimensions, we need to determine 2 relevant directions on that plane. But I can ask you, does this plane equation include the origin? Does the P1 include the origin?
Yeah, I think so.
Huh?
Yes.
Yes, it does, because C1 and C2, they can be 0, so they are in the possible domain to include that. And but the second one, it does not include the 0 or the origin. So if we have the three, now we have a plane, and planes, they are, they can separate the three-dimensional space in two equal halves, okay? So if we have here the x, y, z, this is the x, the y, and the z, we can expect to have a plane that looks like this, including the origin, if we're talking about P1. And then P2, it can be another plane which is shifted away from the origin. So let's consider this one as P2, but this one does not include the origin because it is shifted by a constant value shown here, P. And then let's see. Let's try to see some examples, or at least one. And actually, I also wanted to ask you if it's possible, would it be good for you if we do the lectures, we don't do it 3 hours in a row like now, but if we have one of the hours, we do it somewhere on Monday. Is it possible for you?
Monday we have 2 lectures, maybe Tuesday.
Tuesday is a good time, okay. We can do that. We can try to use the Tuesday.
In Monday we have English this time.
Sorry, can you repeat it again?
In Monday we have English this time.
Oh, this late in the evening? Okay.
Yeah, but on Monday, not on Tuesday.
But we have Friday free.
Friday's free, okay.
I mean, this time.
Okay, actually, okay, I'm going to check the timetable, and we might skip 1 hour of today's into another day. Okay, so they don't sit for 3 hours. And now let's see one example.
I think we have physics Friday.
You have on Friday?
Friday we have 2 lectures.
No, Friday we already have something. I think in Friday we have another 2 courses.
No, I'm going to have a look at Okay, I'll check this again, and I'm going to communicate to you, okay? Now, in the analysis of the planes, it's good to cover some examples because a plane is normally can be defined by a normal vector. So, for example, how actually a plane we can define it by 2 vectors, which are going to be here and here. Imagine that you have one direction like along this pen and another direction along this pen. So you need these two vectors, and you define the plane. But having the same plane, let me ask you this. We have this, and we have these 2 vectors that look at a specific angle. We can have, this is a set of possible vectors which can span, ce mund të spanojnë ose mund të skanojnë të gjithë të fletën e parë që kam këtu. Ose ta bëjmë në dras. So I have these 2 vectors. These 2 span the board, right? But at the same time, these also span the board, and also these span the board. Only these 2 don't span the board. So if they are pointing in the same direction, if the angle between these is 0 degrees or 180, now they don't span. But the moment that they have an angle like this, we can span. So it looks like for a plane, we can have an infinite number of pairs of vectors. Okay, because two-dimensional space, we need two vectors to define the plane. But it's too much. Okay, so we can. And the question is this: is it possible to have a more unique definition of a surface area? For example, let me ask you here, and who is in line? We have Grady. Grady, you have the chance to pick up some bonus points, which I'm going to use it for you in the midterm. Grady, how many surface areas has the cylinder? Grady, can you hear me? If your microphone is not working, imagine you're just losing 10 points for the midterm exam. You go to the closest store, you buy the microphone, a very good one. Huh? Grady? He's just losing it. He doesn't know. Oh, Grady, I'm having problems with my connection. Okay. Can you answer in written? So how many surface areas does a cylinder have? Time is ticking away.
3.
3, okay. You beat it. Now the microphone is working, right? I was hoping to... okay, Grady, test 3. How do you define these 3 areas? Kamuri has a different opinion. He's too realistic.
Two bases and letter surface.
Okay, that's true. But now we can define, but how can we do it in order to, or we can also ask the following. How many surface areas does a sphere have? Let's ask Flamur. Flamur, what do you think?
Infinite.
Sphere. Не топ футболи. Sad superficie 1. That's correct. Flamur, you are right. We have only 1. Because in spherical coordinate system, because we don't have only Cartesian coordinate system, we have also spherical and cylindrical. In spherical coordinate system, you have only the radius. So for example, to define all the surface of the Earth, you need only one radius, which is the distance from the center of the Earth to the surface. So the union of all of these points, it makes up a single surface, because the vector, because we need only one vector to define the whole surface. Now in a cylinder, we have like this. So to define the surface area there in cylindrical coordinate systems, we have one vector which is going to define this surface area here. Then we have another vector pointing in the exactly opposite direction to define this surface area here at the bottom. And then we have also another vector which is perpendicular to these, but this vector which is perpendicular all the time with a single surface area which closes like this, it's called the R. And by the way, some of you might remember that there are these coordinates like R, phi, and Z for cylindrical coordinate systems, but of course you may need to go over a textbook and remember those. But for spherical coordinate system, which Flamur correctly answered that the sphere, or the football ball, it has a single surface area, because here we have the phi and the theta. And only the vector r pointing perpendicularly can define the surface. So counting the normal vectors to the surfaces of an object can help us to correctly identify how many surface areas it has, which means that if we have the board here, where any point on the board can be defined by a pair of vectors like this, or like this, we can uniquely define the board by having a single vector which is pointing like this, perpendicular to it. Now, in order to, to understand this, let's have a look at this example. Let's imagine, I'm surprised how you can see the board, but I cannot see without having a piece of paper. So we have to use.
Yeah, it's getting a little bit quiet right now. It's getting darker.
Okay. So let's imagine that we have a plane P1 or plane P, whatever, which is equal to SV plus TW. Okay, V and W, they are any two vectors. And S and T are two constants. So S and T,
We can see.
okay. Yes, okay. So now let's also define what is the V and T. Let's assume that there are two vectors which look like 1, 2, minus 1. This is one of the vectors. And the other one is minus 2, 1, minus 2, 1, 7. Okay? So we have these two vectors. And then the question is to find the Cartesian equation of the plane.
I'm sorry, Professor. Can we do a short break?
What if we do it like this? We get done with this exercise and we close it for today.
Okay, thanks. That's better.
You know, thanks. We continue like this. There is a very small probability that you might have been standing up the same way I'm doing for the last 2 hours, but it could be possible. If you are watching the stars from the window, find Cartesian equation. Po fakt, nga gjithë klasa, asnjë s'po shikon telenovela në orës më të famshme. Apo jo, pse do të thonë pra.
Shohim telenovela, profesor.
Në ka televizor.
Ne shohim World Wrestling Federation. Po shikon edhe World Wrestling Federation, është interesante se ata janë they are the best. Dhe po mendoj sot how can we beat them in the aspect that kur bëjnë ndeshjet ato, aty ku ulën tifozat, nuk vijnë foto, po vijnë ekrane kështu monitore, dhe njerëzit paguajnë lekët, edhe ne ku shohim World Wrestling Federation, mund shikojnë edhe tifozat aty që bërtasin. Nëse unë sot po mendoja se është i këndshme të rishin klasë duke pa mure, edhe shohësh te kamera ashtu, është i pikë blu aty. Dhe po mendoja tash të bëj foto të gjithë klasës, aty vjetën nëpër banka, të paktën të kem të më duket sikur po shikoj dikën në klasë. Sepse është shumë e habishme.
Ka shpenzime apo punë.
Ashtu thotë, po të mos të them si ne foto të gjithë. Ose bëni një grup foto ju, mund ta bëni edhe në Photoshop, me fjalë. Edhe ta vendos aty te kamera, ta kem më tepër kur jam i vetmi në klasë. Okay, atëherë do vazhdojmë. Pra do gjejmë, let's find the Cartesian equation or Cartesian representation of the plane represented by these two vectors. So that's the question. Now, we know that if it is a line in Cartesian representation, how do we define a line? A line is like this, right? Y is equal to mx plus b. That's all. Now, how is a plane? So this is a line. A plane, it could be anything that looks like this. Z is equal to ax plus by, plus maybe a constant d. Would you agree? So this is how, this would be a plane, because, yes, a plane. And this is a line. So we need two variables here for a one-dimensional set. And here we need three variables for a two-dimensional space or, yeah, we can call it Bashkir, or a set of points. So then, instead of this p, let's write for a moment. Let's write the x, y, z. So we know that this x, y, z will be equal to s times v, and this v and w, let's substitute them here. So we get here s times 1, 2, minus 1. And for the v, we get minus 2, 1, and 7. Then, from these here, we can express the x, y, so we can get here that x is equal to s minus 2t, y is equal to 2s plus t, and the z, the third coordinate, will be equal to minus s plus 7t. Okay? So now, what we can do is that we can remove, so we want an expression that should look like this, okay? So we have to make it similar to this one, which means that we have to combine all of these by first removing the s, okay? So s, the smartest way to remove the s, it would be, the first approach would be, we say s is equal to x plus 2t, okay? And then once we have this s plus 2t, we can get that y is equal to 2 times s, where s is x plus 2t. Okay, so we are substituting this s right here, plus t again, which makes this equal to 2x plus 5t. Okay, so this is the y. And then from here, we can find what is the, we can express the t as a function of x and y. So this is y, and t is equal to what? Is equal to y minus 2x divided by 5. Now, here we have the expression of, so all of these expressions, we can substitute them into the z. So here, z would be equal to minus s, and minus s is, so let's substitute this first part here. We get minus x plus 2t, okay? Maybe it's, no, minus 2t, that's
minus 2t.
Thank you, that's correct. Minus 2t plus 7t, right? And this would be equal to minus x plus 5t. And this is equal to minus x plus 5t plus 5 times y minus 2x divided by 5, and the 5's are gone, and we're left with minus x plus y minus 2x. Okay, so finally we get that z minus y plus 3x, this is equal to 0. Now, it looks like the final equation is this one. Now, let's come back for a moment and let's look at the first expression here that was given initially. Now, we have these two types of planes, P1 and P2. The first one was passing through the origin because it does not have a constant vector which is going to shift it all away from the origin. So, this plane equation, and when we look at this one, this looks like an equation which includes the 0, right? Because their s and t, they can both be 0, and this means that x, y, z, it is possible for them to be all zeros. And then, when we look at this expression, we get here z minus y plus 3x is equal to 0, so they can really all be 0, the problem is satisfied. Now, another major information that we can extract from this expression is that the coefficients of x, y, and z, they define this. They define the normal vector, okay? So here, n, we can define a normal vector n, which is equal to x is 3, y is minus 1, and z is 1. So here we have the, the normal vector. But we have also here something interesting, which is the following. This is the normal vector, and from here, or we can write it here, this implies that the equation of the plane, it can be written as n times x. Or let's write this one vector v. And this is equal to 0. Okay, so do you understand this? This is the equation of a plane. So this is a plane which includes the origin. This is also a plane which includes the origin. They're equivalent because we know that this n, which is 3 minus 1, 1, this is the inner product. The inner product, we make this a row, which becomes 3 minus 1, 1. We multiply with x, y, and z, and this is equal to 0. And I guess we still get the same expression, right? So here we have 3x minus y plus z. This is again the equation of or the Cartesian representation of this plane. We are good, right? Now, this is 3 minus 1, 1. Good. Now, I want to ask you, what would you expect what is the inner product? Actually, let's write this one as x, like position vector x. And we really put there x, y, z. Now, let me ask you this. What is the inner product? And let me have here who is on the... where did we stop? I think the last communication we had, I think I talked with Genti. Genti Haveri, Famori did his part. Genti, can you help us to identify what is the inner product of M with V? Where V is this vector, this one here. You cannot see it? Okay, here.
Yes, I can see the table. Let me do the calculation.
So you can speak, I can write them down.
So n is 3 minus 1, 1, and v is, I cannot see the numbers.
V is 1, 2 minus 1.
The inner product is 3 plus minus 2 plus minus 1.
2 minus 1.
Yes, 3 plus minus 2 plus minus 1, which is 0.
Is this expected? Would you expect this to be 0? What do you think? Any comment?
That's the inner product.
Yeah. Would you expect the inner product of these two vectors to be 0? Can you think this for a moment? Anyone can answer this?
Yes.
Yes. Why could they be 0?
So we first had n, the dot product of n and x is equal to 0. So any value of x, y, and z, which we got from equation like 1, 2, and minus 1, those are the values. So when the dot product of n times any x, y, and z value in the plane is going to be equal to 0, I think.
Well, let's do this one. Let's check if 1, 1, 1, because you're saying that any number is going to get it 0. But we know that those values in the plane is not an infinite number, right? It's a plane which is going to be oriented somewhere, and I'm sure that plane is going to miss a lot of points.
Okay.
Let's try this one. 1, 1, 1.
What if we had, for example, the other x, y, z values? So minus 2, 1, and 7.
Minus 2, 1. Okay, let's do that. Which means that what is n? N is 3 minus 1, 1. And we multiply this, but let's not forget, what you see over there, they are not points in the plane. They are the vectors that define the plane. That span, just canoeing. But let's do this, minus 2, 1, 7. Minus 2, 1, 7. So what do we get here? 3 times minus 2 is minus 6, right? Minus 1 plus 7, you get 0 again, right? Why do we get 0 here again?
Because it's a Cartesian.
Does it happen because it is the unit vector?
No, they are not unit vectors because unit vectors would have a length of 1.
We said that those vectors span the plane.
Yes, correct.
That is why we get 0 every time.
Because, Okay, but why? I mean, yes, but you did not. The key sentence which would make you look right, you did not say.
Do they lie in the straight line?
No, but can I have the previous student?
It forms 90 degree all the time with the plane.
That is the key sentence that you should be using, Angesia, okay? So the idea is that when we span a plane, so let's assume that I have this piece of paper or this plane. The vectors that span this plane are here, okay? Because I want to represent this specific point as a function of this vector. So this vector is lying on the plane, but then the normal to this plane is this. And you are right. Any vector on the plane, dot product with a vector which is perpendicular to the plane should get 0, okay? Because the inner product is a dot product. So if these are I think, for example, if we come back to this definition here, T and V are the vectors that lie on the plane, then whenever we find the normal vector n, each time n dot inner product with V, it should be equal to n inner product with W should be equal to 0, okay? And all of us should have predicted this. We could have predicted that the normal component, which we found here, z minus y plus 3x, anytime this normal with those two should produce 0. Okay? So there is a lot of intuition here. I hope that with a couple of more examples, this should become very clear. But at the same time, I strongly suggest you to go over the textbook, because textbook has very intuitive problems to solve. So you can go over those in case you have any difficulty. You can come and ask, and we can solve them together. Okay? And is there any question?
Profesor, do doja të flisja diçka me ju.
Patjetër. Po.
Në lidhje me shpjegimin e mësimit.
Patjetër, po më thuaj.
Do doja që domethënë të ecit pak më ngadalë. Sepse kur shpjegoni, ju shpjegoni domethënë shumë shpejt dhe këto janë gjëra që i kemi marrë për herë të parë. Edhe nuk arri dot t'i kap aq shpejt se si ecin gjërat, rrjedhën e tyre domethënë.
The first version of the answer would be the following. You just run the YouTube channel on 0.25 speed coefficient, okay? Kjo është shaka. Ne që këto regjistrojmë, është e vërtet. Është dhe kjo gjë që në fakt tu po bëjmë pak aspektin teorik dhe kam përshtypjen që edhe në orën e seminareve disa gjëra do i përsëriti. Edhe unë kam përshtypjen që unë çdo gjë që kam bërë në rast, sot e kemi komunikuar me ju, që do të them jam munduar të kem feedbackun tuaj ose të hes me shpejtësinë tuaj. Nëse është e vërtet për shkakun, në rast kemi përmendur kështu në pak shpejt relativ, kështu pak me duket si shpejt.
Profesor, vetëm herën e parë kemi marrë 7 mësime.
7 mësime? Po, ajo.
7 mësime, ato që më pash tek libri, unë se lexova librin dhe ishin 7 mësime.
Ato janë 7 mini seksione.
Mini seksione, por që merr edhe me YouTube, që ti si ke bërë asnjëherë këto, do të shikoj këto video secilën, më kupton se nuk kuptohen.
Dakor, mirë, Oklea, ke drejt. Shiko, ç'është ashtu që për sa herë që të shpjegoj këtë në klasë, unë ju kam thënë që ju lutem që më ndërprisni ose nëse keni komente ose diçka të paqartë, ju mund të thoni, slow down, kupton? Unë e bëj atë. Në rregull, po të falenderoj që ma thej si koment. Nëse dikush tjetër ka në klasë që mendon që kemi ecur pak shpejt, ju lutem ma thoni, ose rregullojmë herën që vjen. Ne kemi synimin që janë disa elementë për shkak të që ne diskutuam pak për shkak për gjeometrinë ose aspektin gjeometrik të vektorëve ose të planeve dhe të vektorëve dhe të planeve. Menduam që është mirë t'i bëjmë sepse ju ndoshta ju kthjellojnë shumë atë konceptin e hapësirave, how things move in space etj. Por gjithmonë ju lutem më thoni për shkak. Është pak shpejt, më ngadalë etj. Po të falenderoj Tria që më the këtë. Do të pyetje tjetër në gjë tjetër pa qartë? Po,
profesor. Këto vektorët janë gjithmonë pingull? Domethënë e nxorëm 0 këtë dot product.
Po. Shiko, Rubini, okay. Ç'është ashtu? Ç'a thamë? Kur e shkruajmë ekuacionin duke përdorur shprehjen karteziane, këto koeficientet e x-it, y-it dhe z-s, ky është vektori pingull me planin. Pra ky është kjo. Është pingull me ndonjë 90 gradë. Kurse vektoret për cilët ne na duhen që ta përshkruajë të drasën e bardhë, ne mund të mendojmë se kemi drasën e bardhë, mund të mendojmë se kemi këtë copën e letrës që janë dyshek këndim. Vektori që e përshkruaj të drasën e bardhë në mënyrë të plotë, që në anglisht ne e quajmë eskanon, ose fjala më e dur është sper. Për shembull, lejo të shkruaj diçka këtu, pyetja është shumë e vërtetë. Por ne çfarë themi? Për shembull, në këtë ekuacion e shkruajmë kështu, thamë pika p është e barabartë me st ose çfarë thamë sv plus t w. Terminologjia e kanë të formë, themi v, vector v and vector w, they can span the plane. Në rastin tonë, plani është drasa e bardhë, whiteboard, okay? Pra kjo është terminologjia që përdoret dhe i bie v-ja dhe w-ja do të jenë këtu. Ja ku kemi v-ja, këto w-ja. Ky është një çift që eskanon, që do të thotë këtë pikën këtu të drasës, unë mund ta përshkruaj si kombinim i kësaj. Si e bëj këtë punë? Marr 2 copë të sekunder saj, jam përshkruar 2, marr 3, me që mora 3, çfarë duhet bëj? Do të vi çik mbrapsht me këtë, që do të thotë marr minus 1/7 e kësaj. Po vi mbrapsht dhe erdha te pika e interesit. Duke zbritur 1/7 ose në drejt drejtimit, ose për shembull, këtë pikën këtu, si e përshkruajmë? Hajde mundohem ta gjejmë. Këtu kemi këtë komponentin këtu, i shtojmë një flerë këtu. Atëherë marrim të e sjellim këtu vërdall, me që drejtimi është këtu, po të kisha ato do të qenë këtu, që do të thotë, më duhet 1.8 të këtij vektorit fillestar, po e quajtë v, plus 0.7 w. Po kupton këtu? Pra, tani, pa marrë këto vektorë gjithmonë të planin. Tani, ndërkohë që këto vektorit janë këtu në plan, vektori që është pingull me këtë planin shumë është këtu. Dhe sa është shkondi midis pingullit të këtij planit të drasës me këtë drasë, është 90 gradë.
Po, është 90.
Tani, inner product është gjithmonë e barabartë, për shembull, inner product n-ja me v, inner product është e barabartë si e shkruajmë këtë. Kjo është e barabartë madhësinë e n-s, magnitude of n, që shumëzon magnitude of v, që shumëzon kosinusin e këndit teta. Tani, nëse këndish 90 gradë, këtë 0 të dalë. E qartë? Pra, të pyta është shumë e vend, me fjalë thjesht mund ta keni për parasysh, ose ka një copë letër kështu, e keni këtu, ja ku kam 3 letra, cili, ta them me këndin fjalë, cilet e vektorë që e skanoj këtë, unë vizatoj 2 random vektor, këtu i kam. Këto 2 vektorë më mjaftojnë që unë këtë pikën ta gjej si funksion e këtyre, edhe këtë pikën e gjej si funksion e këtyre, e kështu me radhë, çdo pikë këtu e gjej. Mirë, po ndërkohë që këtë këtu, vektori që është pingull me këto, është ky lapsi blu, dhe gjithmonë ky lapsi blu që është pingull me këtë, në cilin ndodhen këto vektorët, nga që këndi 70 gradë, inner product është 0. Në rregull? Kështu pra, okay, shumë mirë. Pra, ta shikojmë pak këtë pjesën kështu. Herën tjetër, shpresoj do shikojmë kushtrime mbi planet ose mbi disa shembuj, mbi planet dhe mbi drecat. Në rregull? Do i pyetje tjetër?
Jo.
Në rregull. Atëherë unë ju falenderoj shumë për vëmendjen. Dhe për një pyetje tjetër, në fakt mund të komunikojmë qoftë me email. Kisha një student që nuk e kisha te lista te Google Classroom. A ka diku nga klasa juaj që nuk është i shtuar te Google Classroom? Ndoshta jo, okay. Atëherë nëse kështu është situata, atëherë ju falenderoj për vëmendjen.
Faleminderit juve.
Mirupafshim, të kaloni mirë. Edhe të kaloni
Mirupafshim.
Mirupafshim.
Mirupafshim.